Hello again everybody, and welcome to part 2 of Sedimentary Rocks and Environments. Okay, so this is where we finished part 1. So as you can see, we have a very simple diagram here that's running through the basic process of the formation of a sediment. Now remember, in this particular instance they are essentially showing the transportation of a sediment by water, but of course remember, it can also occur by wind, ice or gravity. So so what's the process we start with? Well, the process we start with over here is of course weathering. And weathering is simply the weakening of a rock and essentially causing it to fall into chunks. And those chunks will obviously gather and they will slowly but surely be broken down, they'll be eroded to the point at which they can be moved by one of the four mediums. Now obviously during that process the rock will be moved along, and during that process it will be reworked. As I think I've already mentioned, the transportation of a sediment will cause the clasts to change. It will cause them to change physically, so it will affect what the size of the clasts are, how well rounded the clasts are, and how well sorted the clasts are, what's the size range. It will also affect the class chemically. So it will, for instance, get rid of minerals which are chemically unstable. So a mineral like olivine, which really doesn't get on well with water, will break down very, very quickly. In contrast, a mineral like quartz, which is far more robust in a water-rich environment, will be absolutely fine. And so the longer the sediment gets transported for, the more olivine is lost, and quartz obviously becomes more and more dominant in the sediment over time. Eventually, obviously, our sediment will get deposited, and during the process of deposition, as we said, it will be deposited as layers, and over time the layers will get, a layer will get buried deeper and deeper and deeper in the stack, and during that process of being buried, the temperature and pressure will go up, so it will be buried, compacted, and eventually liquefied. Now in this diagram you can also see the water is moving across the surface, but the water is also moving in below ground level as well as groundwater. When it's moving along the surface, it's transporting the weathered rock as both a mixture of solid particles, the clasts, and also material which is dissolved within the water as ions. When the water is moving underground as groundwater, it's obviously only transporting weathered material as ions. Okay, so weathering occurs in one of two ways, physically or chemically. So let's think about physical weathering or mechanical weathering. So as we can see here, mechanical weathering essentially requires some kind of process that actually physically forces the rock into pieces, essentially like you walking up to a cliff face with a sledgehammer and repeatedly hitting it. That is a mechanical process. So let's have a think about what kind of processes can essentially cause a rock to break up. Well, the first one is fracturing. Now fracturing can occur in response to several different processes. One of the more common ones is as the rock is exhumed. So a rock's held underground. It's held underground for millions of years and it's got lots of rock around it that's putting lots and lots of pressure on it. And so as you exhume that rock and you bring it to the surface of the earth, the pressure obviously begins to decrease. And so what happens to that rock? Well, that rock that was under a lot of pressure suddenly can begin to expand. And as it begins to expand, it will crack. So that's one of the ways in which we can form fractures. We can also form fractures simply due to changes in temperature over extended periods of time. So if you've ever been into a desert environment, what you will know is that during the day in a desert environment, it can get exceptionally hot. So the rock gets heated up, heated up, heated up, and heated up. However, during the night you will also know the temperatures can drop very, very quickly, and sometimes they can actually get quite low. And so all of a sudden you have your very, very hot rock, which is suddenly exposed to a very rapid decrease in temperature. And so your rock, which was expanding because it was being heated up, all of a sudden finds itself contracting very, very quickly. And so that can also lead to your rock fracturing. There are several other processes, but I'm just going to go with those two for now. So another way we can break our rocks up is through frost and mineral wedging. So frost wedging is quite straightforward. It occurs in environments typically where water will be able to freeze, normally during the night. So we have a crack in our rock, and during the day that crack will fill with liquid water. Now as we go into the night, the temperature begins to drop and the liquid water in the crack begins to freeze. And I'm sure you guys know that frozen water has a greater volume than liquid water. So as the water begins to freeze, the volume increases. And so the water begins to put pressure on the rock either side of it. The ice water, should I say, begins to put pressure on the rock either side of it, and it physically begins to push the joint apart, make the joint wider. Now, one time isn't going to do it, but imagine that happening day after day after day after day for a prolonged period. Well, eventually, that's going to weaken this joint so much that this piece of rock is simply going to fall off. Now, what about mineral wedging? Well, mineral wedging is caused by the movement of water along the fracture. So as the water moves along the fracture, it can deposit minerals as it goes, and slowly over time it will deposit more and more and more minerals. And so this will mean that over time, as you deposit more and more minerals, the crack simply gets forced wider and wider and wider, and eventually that can once again cause this piece of rock to pop off, and away it goes. Another mechanism through which we can have mechanical weathering is by plants. So if you've ever been to an area where there's relatively thin soil, so you will know that plants will exploit any kind of crack in the rock to stick their roots into so they can anchor themselves. And so the process of the plant forcing its roots along a crack in order to anchor itself to the ground, well, obviously that pushes the crack open. It weakens the rock, and it can eventually cause the rock to fall to pieces. The final type of physical weathering is going to be abrasion. And abrasion is more commonly described as sandblasting. So once again, you're in a desert environment. During the day, the sand can get picked up by the wind, and if you've ever been to a beach, you will probably know that if the sand gets picked up by the wind, it can really move at a pretty fair speed, and when that sand hits your legs, it can actually hurt. So imagine that happening to this cliff here. Sand gets picked up by the wind and it's constantly being launched, pummeled against this cliff face right here. Every time a sand particle hits that cliff face, it's going to knock off a very, very small piece of rock. And so that's obviously going to slowly but surely wear down this cliff face, and eventually it will abrade it away or destroy it. So those are some physical methods by which we can weather a rock. So then we have chemical methods by which we can weather a rock. And the four most common chemical methods are dissolution, oxidation, biological reactions, and hydrolysis. So chemical weathering essentially will break down, will weather the rock through chemical reactions, essentially weakening the rock, dissolving the rock. Alright, so one of the more common ones is dissolution. And that's simply when a mineral dissolves away in the water when it comes in contact with it. So a classic example of that is a limestone. When a limestone is put in contact with water, very small quantities of the limestone will just dissolve into the water. The calcium ion and the carbonate ion will essentially come off the rock, and they will dissolve in the water. At which point these ions can then be carried away, dissolved in the water, the surface water, so rivers and streams, or they can be carried away in groundwater. And so slowly over time, imagining that happen day after day, year after year, slowly but surely your limestone will get degraded, it will get weathered away. So the next method of chemically weathering a rock is through hydrolysis. And that's when our minerals react with water, causing those minerals to break down and form new compounds. So a classic example of that is a rock like a granite. So a granite is very, very rich in a mineral called quartz. You're probably familiar with it. Now quartz is very stable, so quartz is fine. But it also contains other minerals, and one of the other minerals it contains is a mineral called potassium feldspar. And it also contains another mineral, which are these black specks here, called biotite. Now, biotite does not get on well with water. So when the biotite comes in contact with water, the biotite will react with that water and it will break down, and eventually it will produce clay minerals. The same thing will happen over a much longer time scale with the potassium feldspar. The potassium feldspar over a prolonged time period will break down and it will form clay minerals. Now obviously the process of these minerals, the biotite and the potassium feldspar breaking down to form clay minerals, are going to weaken the rock, and so that's going to make the rock far more likely to degrade and fall to pieces, at which point you have a chunk of rock, then it can start being transported away as a clast. Next we have oxidation. So oxidation is, shock horror, when your minerals react with oxygen in the atmosphere. The best type of mineral to do that are iron-bearing minerals, because iron really wants to bond itself to oxygen. So if you do have an iron-bearing mineral in your rock, that iron-bearing mineral will love to react with the oxygen in the air, and obviously that will cause a chemical reaction. So your iron-bearing mineral will react with the oxygen, and the iron mineral will break down because of that reaction. Well, once again, just like hydrolysis up here, if that happens enough over a long enough time period, the loss of those iron minerals will weaken your rock, and eventually that will cause your rock to break down into chunks, should I say. So here we have a few examples of the process. This is dissolution going on. You can see this very pitted surface we have here, which is being caused by the limestone breaking down and dissolving in the water. You can see we have the same thing happening over here. We can see over time this limestone is steadily breaking down. It's being dissolved away. In contrast, this granite headstone over here is in a far better state, because the minerals within it are far less chemically reactive. So we can see here we have rust forming along these cracks in this rock. This is an example of oxidation. And here we have in this piece of granite, you can see the original granite itself is nice and fresh there, but this granite here has been exposed to water and it's undergone the process of hydrolysis. So the minerals within the granite are breaking down due to reactions with water. Now the final type of reaction we have are living organisms. So living organisms like lichens and essentially any plant with roots will have to protect themselves. Now one of the ways that plants protect themselves is they cover themselves in a layer of slime. So if you think about a root that when going into the soil, soil is, for want of a better way of describing it, actually quite a bad place. It's full of bacteria which can in theory do harm to the plant. So one of the ways the plant gets around that is it will cover its roots in a slightly acidic substance to make it far more difficult for the bacteria to go from the soil into the roots and infect the plant. And now obviously the chemical compounds released by the plants when they're alive and also released by the plants when they die and decompose are going to react with the rocks. And so if we just go back for a second to this diagram here, the roots of these plants here are going to be covered in this slightly acidic substance to protect the roots, and that's obviously going to react with the rocks, and that's going to cause chemical reactions. When these plants die as well, the decomposition of the plants will also produce a range of compounds, some acidic, some alkaline, which can also react with the rocks, once again causing them to break down over time. So plants essentially can break down rocks when they're alive, and they can break down rocks when they're dead. Okay, so once we actually have our sediment, it's going to be transported, and I do apologize, this diagram is pretty horrendous, but it does kind of get across what we're aiming for. So once we have our sediment, it's going to be transported, and typically a sediment will be transported from a high relief terrain to a low-lying depression like an ocean or a sea. Now most of the time that transportation takes place by water, but as we've discussed, it could also be via air, ice, or gravity. So we have our sediment here produced by weathering and erosion. It gets transported, it gets deposited, and it gets liquefied. And you can see that the weathering and erosion is going to happen up here in the high ground. Transportation was going to occur as the transporting medium comes downhill under gravity. Eventually, the sediment itself is going to be deposited, and then obviously lithification, compaction, well, burial, sorry, compaction and lithification is then going to take place. So, what are the transportation characteristics? Well, as our sediment is transported, we're going to see changes in its size, its shape, and its sorting. So, first of all, what's class size? Well, when we describe class, we have several terms. So, if I walk up to somebody and I start talking about sand, as a geologist, I'm not talking about what the sediment is made up of. So normally when you go to a beach and you pick up the sand, you'll typically have something that's mostly dominated by quartz, a little bit of feldspar, and a few other bits and bobs. And so you would assume, right, well, if I'm talking about sand, obviously what I'm talking about is quite a lot of quartz, a little bit of feldspar, and a few other bits and bobs. But I'm not. As a geologist, when I talk about sand, I'm talking about a size classification. So if you look here, sand is actually a size of clast. So it doesn't matter what the clast is made from. All these clasts here could be diamond. They could be solid gold. It doesn't matter. It's just based on how big they are. So in geology, going from smallest to largest, the range of clasts goes clay, silt, sand, with obviously fine being the finest, medium the intermediate, and coarse being the coarsest. Then we have pebbles, also referred to as gravel. I tend to use the term gravel personally. Then we have cobbles, and then we have boulders. And so each one of these terms will have a size range associated with it. So here we go. So you can see clay, silt, fine sand, medium sand, coarse sand, gravel, and then obviously here we have cobbles and boulders. And you can see that each one of these sizes, each one of these types of sediment, or sizes of sediment, has a size range associated with it. So if I'm talking about a sand, I'm talking about something that has to be between 0.06 millimeters and 2 millimeters. So if I have a particle, a clast of those, that diameter, it will fall somewhere in the sand category. If I have a particle that's greater than 64 millimeters, I would classify it as a cobble. Okay. If I have a clast which is 270 millimeters, I would classify that as a boulder. So that's the first thing that will change. So as we transport our sediment, the size of the clasts in our sediment will change. What else will change? Well, the rounding of our clasts will also change. When our clasts first form and they're first weathered from the rock face, the clasts will be quite angular. If you've ever been to a mountainous area and you've seen landslide deposits, for instance, what you'll notice is the pieces of rock in that landslide deposit tend to have lots and lots of sharp corners. They are angular pieces of rock. However, over time, as those pieces of rock get transported, the pieces of rock bang into each other, they rub against the riverbed, for instance, and these sharp corners get knocked off over time. And so the longer your sediment gets transported for, the rounder and rounder it becomes. So over time, as your sediment gets transported, you will lose the angular clasts, and those clasts will become more and more rounded. The final thing that will change as we transport our sediment is what we refer to as the degree of sorting. Now, once again, going back to our landslide deposit, if you're in a mountainous area, what you'll notice is made up of, big pieces of rock, boulder-sized pieces of rock, cobble, gravel, sand, silt, and clay. There's the full range of class sizes in that landslide deposit. It's a very poorly sorted type of sediment. In contrast, as your sediment gets transported over time, well, big clasts will bang into big clasts and they will knock pieces off each other, and they'll get steadily smaller and smaller and smaller. The more times a clast bumps into another clast, the more pieces they'll knock off each other, and the smaller and smaller they will become as they are transported. And so normally that means as your sediment gets transported, the degree of sorting will improve. So the size range will become tighter as the sediment is transported. Okay, so what we can see here is you can see we have 3 pictures of sediments. So I'm just going to have a look at this here. Okay, so here we quite clearly have an angular sediment. You can see there are lots of sharp corners on these pieces of rocks. These are angular clasts. A clast is a piece of rock or mineral. So each one of these is a clast, and these clasts would be defined as angular. Now at the other end of the scale we have clasts which are nice and rounded. So you can see, look at this clast right here, no sharp corners whatsoever. It's trying to approach a near perfect sphere or ellipse. That's what it's aiming to achieve. So we can tell that this sediment here has clearly been transported for a long time because all the sharp corners have been knocked off the clasts. In contrast, this sediment over here, where you have all the sharp corners still on the clasts, that tells us this sediment has not been transported very far at all. Now obviously there's going to be an intermediate between those two, and that's referred to as, in this diagram it's referred to as partially rounded, although it's typically referred to as sub-rounded. And sub-rounded clasts will have features of these two extremes. So you'll see, for instance, you have clast here which has a relatively sharp looking corner there. In contrast though, this corner here is quite rounded. So when you have a mixture of these two, you're dealing with sub-rounded clasts. And so the moral of the story is, when you transport a clastic sediment, so a sediment that contains pieces of rock and mineral, the longer you transport it for, the rounder the clasts become. The less time you transport it for, the more angular the clasts will be. And now obviously that's quite important to a geologist, because if I come along and I see a sediment, or sedimentary rock should I say, that's made up of these rounded clasts, well, I know that whatever process deposited those rounded clasts must have been transporting that sediment for a long time. In contrast, if I see a sediment that contains lots of angular pieces of rock, angular clasts, well, I know that whatever process deposited that sediment was not transporting those clasts for an extended period of time. Okay, what about sorting? Well, you can see we have, once again, 3 different situations. Here we have a very poorly sorted rock. You can see we have some boulders here, we have some cobbles, we have gravels and sands here, and there's going to be silts and clays mixed in there in between the gaps of these larger pieces of rock. That's a very poorly sorted sediment. It contains a very broad range of class sizes. Now in contrast, if we go to the other end of the scale, here we have a very well sorted rock. You can see when you look at this, all the clasts are the same size. There's no obvious variation. That's a very well sorted sediment. The class sizes are very contained, very limited. And then once again, there's going to be an intermediate between these two end members, which is going to be moderately sorted. So there's going to be a slightly tighter range of class sizes, but it's still not going to be quite as well sorted as a sediment that's been transported for a very long time. Now, as I say, the longer you transport a sediment for, typically the better sorted it will become. So over time, these large pieces of rock will bang into each other, they will break down, and they will form smaller pieces of rock. So the larger clasts will get steadily removed and removed and removed, and the size range of the clasts will get tighter and tighter and tighter over time. And so a sediment, for instance, in a desert will have a very, very well sorted sediment, because desert sands get transported over huge distances. And so that sediment will have had a very long time to get rid and break down the larger clasts, and so the size range gets tighter, tighter, and tighter. Okay, so we've discussed rounding, we've discussed size, and we've discussed sorting. So the longer you transport a sediment for, the rounder the clasts will become, the smaller the clasts will become, and the better sorted your sediment will be. Now, there are a few things that will affect the speed at which these processes occur. Now, the first one is going to be the agent of transport. Okay, so if the agent of transport is quite energetic, it's clearly going to cause the clasts to become rounded off faster. So, for instance, wind. Wind is quite an unenergetic transporting medium. So it's going to take a very, very long time for your class to essentially become rounded, become smaller, and become better sorted. In contrast, water is a far more energetic medium. So it's going to cause your class to become rounded, smaller, and better sorted considerably faster. There's also obviously going to be the strength of the current, which is related back to the transporting medium. The stronger the current, the faster the rounding will occur. So if you think about it, if you think of a slow flowing river, well, the class, they're just going to occasionally bang against each other very slowly every once in a while. So rounding is going to take quite a long time. In contrast, think of a fast flowing mountain stream. The class are constantly being bang, 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 bang. They're constantly banging into each other. And so that's going to cause them to round off, become smaller and better sorted much, much faster. The strength of the current is a direct reflection of the steepness of the slope. The steeper the slope, the faster your water is dropping. And so the faster your water is dropping under gravity, the stronger the current. The flatter the slope, the more slowly your water is dropping, the weaker the current. So you can see that steep slopeness, strength of current, and the transporting agent will all affect how quickly your clasts are physically changed. So what about deposition? Well, do you know what? This is the perfect time to stop part 2. So once again, stop the presentation, get up, have a walk around, go and get a cup of water, tea, coffee, whatever, and please come back for part 3.